Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on interpretability and what's sometimes called XAI or explainable artificial intelligence. It's part of the course Analytic Methods for Lawyers, and it's intended both for lawyers and for really anyone who's interested in the field of machine learning and artificial intelligence. The predictive models that we've seen so far in this course are sophisticated and often they perform well, but there is a price for complexity. The reasons for the model's predictions or classifications often become essentially impossible to discern either en masse or in individual cases. And understanding how a neural network works or how the gradient boosted trees algorithm operates requires a level of mathematical sophistication and intellectual patience either never possessed or not retained by a significant fraction of the adults on whom these algorithms might have adverse consequences. And so a movement's grown up in recent years for XAI, explainable artificial intelligence. The idea is to come up with approximations of models or visualizations of models that may provide those affected by them some idea of how they operate. This essay, and this video, explores XAI in the context of prediction. I'm going to show you the breakdown algorithm, but I'm going to suggest that various solutions to the interpretability problem, except perhaps symbolic regression, do not hold up well, and that in fact, both in prediction and classification, many serious issues remain. First of all, the simplifications the solutions require will often make the outcome of the emulator different from that of the predictor, reality, or both. And second, because many of these simplifications rely on localized models, that is, models that apply only to a certain subset of the population, issues are likely to develop between conflicting results reached by different localized models, and you're going to have to impose some distance metrics that no one may understand anyway, in order to make it work. In short, I would say as of 2021, XAI remains more of an aspiration, and a worthy aspiration, than a fact. It's still very much worth studying, and we'll do that here. The other thing I can tell you is actually XAI serves as a good review of much of the machine learning component of this course. I'm going to execute the first line of code here, and it's going to take much longer than you think it should to evaluate. That's because there are what are called initialization cells in this notebook. What's actually going on there is actually we're creating a little trained neural network that's going to serve as this function f that I'll talk about in just a moment. So let me start evaluating the code and then I'll explain what's going on. All right. And because I don't have a clean kernel, it actually happened real fast. Let me clean out the kernel here. All right, now let's do it. Yes, I do want to evaluate the initialization cells. All right, so we're going to start with some data. And I'm going to imagine a scenario in which we've got 20 features. To make life easy, all the features are scaled similarly, and in fact they're all drawn from the same normal distribution, this basic 0-1 normal distribution that we've seen for many, many lectures now. I'm going to give ourselves 1,000 cases, and the idea is we want to try to figure out, here are features, and I'm going to compute our targets using the true function f that got computed down in those initialization cells. So we'll have features and targets in just a moment. We don't know what the function f is. That's why you're not seeing it. It might have random noise. It might be deterministic, but so complicated that it seems as if there's noise. In any event, it's going to be a highly nonlinear function. That's one thing I will tell you. All right, so there we go. We've got our targets. I'll do the same thing and create some test data. Same distribution, create 500 of them, and we'll create targets using that function f. That's sort of our mystery that we're trying to figure out. F is kind of the real world. All right, now, suppose we want to develop a predictive model on our training data that we want to deploy in the real world. We might really want that model to be accurate because there might be scenarios in which the cost of inaccuracy was very, very high. So we're going to experiment perhaps with some prediction models. And here you're going to see me use a bunch of different prediction models and see if I can find one that seems to work pretty well on our data. There's nothing really new here. As I said, this is a little bit of a review of what we've done in the course. So the first thing I'm going to do is I'm going to use the Wolfram language predict function to use AutoML. I'm not going to tell it what method to use to make the prediction. I'm just going to tell it, look, here are the features, predict the targets, and I don't need to hear anything from you. And you figure out what method to use. So, fine, this shouldn't take too long. We've got 1,000. And as it turned out, it used gradient boosted trees, which is a nice snazzy algorithm that we talked about earlier in the course. And so we've got some model. And now what I'd like to do is see, well, how well does that model perform on data it's never seen before? So it's never seen the test features or the test targets. And I'm going to compute an R-squared value on it using predictor measurements. So we do that, and we get an R-squared of 0.50. Not bad, not great. But that's our model. All right, let's try random forests. Maybe we'll do better with random forests. Only thing I have to change is to force the method to be random forest. Otherwise, I can just use predict. And away we go. We've got our random forest. Let's see how the random forest does. And it's there at 0.416, not quite as good in R-squared. We could try nearest neighbors. Well, we have look at who the nearest neighbors are, and they kind of vote, and we average. Let's see how that does. And not so great. How about we make a neural network? So we'll just create a little net chain here. We'll normalize our batches. We'll keep this thing at 20. We'll do a nonlinearity. We'll do some dropout. We'll do another linear layer. We'll do a nonlinearity. We'll do some dropout. We'll boil it down to 10 with a linear layer. We'll do another nonlinearity, this time a ramp rather than a tanh. And then we'll boil it down to one value, which will be interpreted as a scalar. So that's our neural network. Not the simplest neural network you've seen. And also, certainly after GPT-2, nothing's ever going to seem like the most complicated neural network you've ever seen. So there's our network. We can take a picture of the network using there's a little visualization of our network. This is all old hat. You've seen this before. And we're going to train our neural network now. There's our architecture. Here's how we're going to do the training. We're going to get back a net train results object. We'll go for 500 rounds. We'll use 10% of the data just to make sure we're not overfitting. And we're going to stop training when the loss on the training data doesn't decrease after 50 rounds. That's our level of patience. So we discussed this in the video on training a neural network. We're going to let it go. There's not very much data. This won't take too long. There it goes. Go, little neural network, and it's done. And you'll see it doesn't overfit. The orange line is right on that blue line. Okay, we can get our trained model from the net train results object. And let's see how our neural net does in predicting data it's never seen before. And this is really the best. It's not way better than gradient boosted trees, but it is a little better. You know, all the methods we just used are pretty complicated. They're not things you can explain to a sixth grader. We could try some simple models, linear regression, decision trees, see how they work. If those work well, we might not need to do fancy XAI. We might be able to use linear regression, which you can usually explain to people as kind of a points system. You know, you got 28 points for this and 31 points for that. They're kind of additive models that they may not understand how you got the coefficients, but people understand how to add up numbers. So let's force the method of prediction to be linear regression, see how it does, see how it performs on data it's never seen before. An R-squared of 0.33, not terrible, but we're not competing with gradient boosted trees or with our neural network or with our random forest. Well, what about a shallow, just a decision tree? A shallow decision tree is explainable. I'm not going to force it to be shallow here, and let's see how a decision tree copes with our data here. We're going to see that it is going to do really poorly on the data it's never seen before. In fact, the R-squared is actually negative, which takes a special type of badness. The reason I believe this is happening is we have a highly nonlinear function, and decision trees, as you may recall, are very prone to overfitting if you don't calm them down. And I think we have a hyperactive decision tree here that's chasing noise, and then when it sees new data, it gets totally confused. So let's just compare our methods that we've done so far. And you can see that we've got two methods that work pretty well. A neural network and AutoML, which in fact is choosing gradient boosted trees. We've got random forest taking the bronze. So because we really want to get this right, we want to predict as well as we can, we want to have as little deviation from the truth as possible, I'm going to assume for the remaining chunk of this video that we're going to use neural network as our machine. That's what we're going to deploy to try and predict reality. And that reality could be whether we're going to keep someone in prison, whether they're going to get a kidney, whether they're going to get into law school, almost as important, or get a job. And because I'm going to deploy this model, I'm actually going to rename NN, which up here someplace is what I called our trained network. I'm going to just now call deployed model to be our neural network. So there it is. Okay, now imagine we have an inmate. I'm just using the prison example because we spent some time on that in our study of classifiers and discrimination. Again, if that doesn't excite you, think of other high-stakes areas where one might want to deploy machine learning, and then one might feel obligated to explain what the heck the machine was doing to someone who was adversely or even positively affected by it. So let's create a sample inmate, and I'll seed our little random number generator, and then we're going to make a radial axis plot of the 20 features of our inmate. You'll see it's the same distribution I used before. So it's just like adding one more to the training or test data. And there is a picture of our lovely inmate. And now we could see, hey, what does our model say about this inmate? And it says, oh, that model, our inmate's a negative 0.08. And that might be a disadvantageous score. Maybe they need, a positive number. Maybe they need a 0.25. And so the inmate might well say, hey, how come I scored so poorly? I want you to explain it. Well, we know what to do. We just say, hey, get on YouTube, watch, 30 hours of videos for this course. Hope they have a strong high school mathematics education or some math courses in college where they learned about matrices and the like, calculus a little bit, and they could follow it. Well, of course, they might have to do the exercises, but I'm being facetious here, obviously. That's quite a burden on someone to explain something. So if they were to go through it, they might develop some mild degree of trust in the ability of neural networks to make valid predictions on data they'd never seen before. But in reality, I think for most inmates, and I'm not picking on inmates here, this would be kidney recipients, law school applicants, etc., that educational process is infeasible and unwanted. Indeed, the inmate might think that watching 30 hours of videos for this course is worse than prison. But in any event, you can imagine saying, hey, go watch 30 hours of YouTube videos as not being a very satisfactory answer, and they still want to know, hey, why did I get turned down? Now, one thing to remember when we're talking about this is they might not do much better with a human. The human might synthesize some reasons that weren't exactly true. Maybe they can't remember why they made the decision. Maybe the reason they made the decision is not something they care to admit because it could be subject to criticism. Or they might say, and I think with some truth, that at bottom it came down to an intuition based on experience, and it's kind of hard to articulate what it was exactly that led them to score something that way. So I do think sometimes that before demanding XAI, we should demand XHI, which is explainable human intelligence. Nonetheless, maybe we could say, all right, I'm not going to explain you the theory behind neural networks. But I will tell you to look at the formula. There is a formula. A neural network does have a formula, and there are just 1,141 parameters in our network. And maybe you could stick that on a spreadsheet, but the reality is no one's able to follow a formula with 1,141 parameters. And, from what you've seen, that's not even a particularly complicated neural network. Supposing you ask GPT-2, hey, why did you say actual was the next word in a sentence? You're going to ask it about, 100 billion parameters, or ask GPT-3 about its 175 billion parameters. I don't think that's going to be very satisfactory. By the way, that's how you figure out how many parameters are in the model. And so in the inmate, our jailhouse lawyer inmate is going to say, hey, you haven't satisfied Judge Henry Friendly's ninth element of procedural due process, which is the availability of a statement of reasons, because you may have said reasons, but they're not anything anyone can understand. It's as if you stated the reasons in Basque or Ukrainian, and they might even cite Wolf versus McDonnell, which actually involves prison, which said that there must be a written statement by the fact finders as to the evidence relied on and the reasons for the disciplinary action. And I have doubts whether just plopping a neural network down is going to satisfy Wolf versus McDonnell. I'm not going to go through European regulations here, but the EU has developed some fairly strict requirements about artificial intelligence explaining itself, and there's a whole, course on how to evade or comply with those. And even if we had a well-educated inmate, that might be the worst situation, because they might say, hey, you got a neural network, you got a gradient boosted tree, they perform roughly the same on the inmates in terms of accuracy, but do they actually give the same result? And so let's test that. Let's test our deployed model and AutoML on the test features and see the extent to which they agree with each other. Okay, let's do a little histogram 3D of that. And you'll see this is where everything would be if they all agreed on the blue plane. And you can see that, yeah, there are people on the blue plane. That's where the two models agree. But you can also see instances where the models actually disagree. And in fact, we can make a plot of the extent of the absolute value of the disagreement. And we're going to make what's called a survival histogram, which looks at the number of cases in which the difference is bigger than some threshold. And we can see there are actually quite a few cases where the difference is greater than 0.2. And 0.2 might be, the difference between staying in prison for X number of years or getting out on parole or having an extended sentence. And so the well-schooled inmate who had watched my 30 hours of video might ask that this analysis be done and be a little disturbed that this is all not as deterministic as one might believe. So it's against these problems that a new field has developed in recent years, XAI, and the idea is to develop algorithms that explain what the machine did. And as we'll talk about, it's a great idea. We're going to talk about the progress, and we're also going to talk about some pretty serious limitations of this methodology to date. But just so we're clear, what we're trying to do is not predict reality. We did that already. We built our neural network that predicted reality. Now what we want to do is come up with a simple method of explaining what the machine did. And so, if the machine is close to predicting reality and our emulator is close to predicting the machine, well, then we can offer a decent explanation. To the extent that either of those links break down, we've got a problem. All right, but maybe it's possible. The first algorithm and the main algorithm I want to talk about is called breakdown, or it's actually a little variant of something called breakdown. It's a time-consuming algorithm, but it works decently and it produces a nice picture at the end. All right, so here we go. This explanation of how the algorithm works probably requires more than a 6th grade education, but here we go. You start with the features that were used to train the machine, or you might choose just a subset, some of the rows of those features. Okay? And what you're then going to do is compute the mean value of the computed target for those features. So you're going to run your deployed model against those features and come out with, a bunch of predictions, and you're going to compute the mean. All right, so that's basically just computing the mean target value for everyone in your data set. That's not particularly helpful to explaining, hey, why did this inmate get this score? So here's what we're going to do. We're going to choose a column of the features, and we're going to replace the values of the feature in that column with the actual value of that chosen feature for the particular person for whom an explanation is desired. That person I call the subject. So what we're going to do is, let's say our subject has a value in column 17 of 0.4. What we're going to do is we're going to take that 0.4 and we're going to stick it in every single person's column 17. Okay? So we're gradually going to make everyone in our data set look like our subject. So we now have perturbed data. We have our original data, but we've plugged in the subject's value for a certain column. Now we're going to take our deployed model, our machine, and compute the mean value of the targets with the perturbed data. Presumably that's going to be a little different than it was when the data was unperturbed. The difference between the mean that I just calculated and the mean that I previously calculated is said to be the effect on the subject of the feature that got replaced. By plugging in that feature, on average, it produced a certain result on the target. Okay? Next, choose another feature, another column. Okay? And now replace the values in that column with the features of the subject in that column. So if it's column 8 and our particular inmate has a value of 0.9 in column 8, now everybody's got a 0.9 in column 8, in addition to the change in column 17 that we already did. So now use our deployed model, our machine, to compute the targets and compute a mean of those targets. That difference between that mean and the one preceding it, when I just replaced column 17, that difference in the means is said to be the effect of column 8, of feature number 8. That's how much change it made. Okay? And you keep doing this onwards and onwards until in the end, every single person in the data set is the subject. They have exactly the same values as the subject. So let's see this in action. Okay? What we're going to do is I'm not going to do it on everybody at first. I'm just going to take the 25 people who are most like the inmate. All right, there they are. And it's a 25 by 20 matrix, 25 because I picked 25 people, 20 because each person has 20 features. All right, let's calculate their mean value of applying the deployed model to the neighbor's 25, and we'll subtract that from 0, which you realize is going to do nothing, but you'll kind of see why I'm subtracting it in a moment. All right, so there we go. That negative 0.215 is our baseline. That's what we get by even having features. If we didn't have any features at all, presumably we'd just guess 0. We wouldn't know any better. So you can think of this as the baseline. Now, as I said, let's take feature 17 randomly. I didn't pick it randomly, I just picked it, but it could be random. And what we're going to do is we're going to write some code here that takes all the values in column 17 and replaces them by a constant, which is the value in column 17 for the inmate. Okay? So we're going to use subset map for that, and we get another 25 by 20 matrix. Okay, we'll call that neighbors 25 v1. Let's take the deployed model and let's apply that to neighbors 25 v1, compute the mean target, and then subtract from that the mean that we previously had. And we'll call that M1. Okay, and that basically is the effect, which is not very much, of feature 17. All right, let's do it again. Now, let's take neighbors 25v1, and let's take all the values in its 8th column and replace it with whatever our inmate has in his or her 8th column. So we do that, and we get neighbors 25v2, another 25 by 20 matrix. We compute. We apply the deployed model to the doubly perturbed data. It got perturbed once by changing column 17. It's getting perturbed twice by changing column 8. We compute the mean of it, and we subtract from that M1, the last mean we computed. And this is the effect of feature 8, which you can see is actually considerably bigger. All right, and we could keep doing that and keep doing that, but you can see why at this point I might want to write some code. So I'm going to write a function, model prediction differences. It's going to take our model, that's our deployed model. It's going to take our features, that's going to be neighbor 25. It's going to take our subject, that's inmate. And it's going to take omega. What's omega? That is the order in which we're introducing variables. So here it started 17, 8, and it's going to pick numbers, it's going to pick a permutation of the set 1 through 20 and just go through that. And you can basically see the intuition here. There's that subset map thing. Remember what fold does? The idea of fold is you have a state, it encounters new data, that changes the state, it encounters new data, that changes the state. And so we're going to get a series here of data sets, each of which is 25 by 20. What we'll then do, that's called data sequence. We're going to map the model over that data sequence and then compute, that's going to produce a bunch of targets. We'll compute the mean of the targets. So at this point here, we've got all the means. I remember how I started with 0, so I need to start it with a 0. That's what the prepend does. And differences just computes the sequential differences. So if I have 1, 4, 9, the differences are 3 and 5. And then we'll just make a little thing where the first element is the first element is all of the variables in order, but I have to start with baseline so that I deal with that first instance, and they all get threaded together. So I think you'll see this actually in action here. I'm going to use model prediction differences, and I'm going to take our deployed model, neighbors 25, our subject is our inmate, and we have a random sample of columns in which I'm going to start perturbing things. And you can see, okay, on average, the baseline was 0.215. Every time I hit column 11, on average, it was a 0.0026 difference. Column 1 resulted in a negative 0.02 difference in the mean, etc. Now, if I add all of these numbers up, it should be pretty darn close to exactly the same thing as if I deployed the model on the inmate, because this is basically trying to break down, thus the name, the score of the inmate into the effect of these various features plus a baseline. So if I take all of these part 2s of these expressions and add them up and subtract off the value when we actually apply the model, I should get something that's really close to 0. And I do. I get negative 2.89 times 10 to the negative 8th. So it's good. And you might have thought, great, we're done. But we're not. Because if I do this computation again, I'm going to get a different result. Why am I going to get a different result? It's because the effect of perturbing any column depends on the order in which we're doing the perturbations. If I do 4173, that 3 is going to have a different effect because it's been preceded by 417 than if I did 3714, because then the 3 would come first. So, and let's just see that. And if you look, you're going to have to, let's just look at this. Number 3 is a 0.019, whereas here 3 was a 0.027. And so what do we do? And the answer is, well, we could just take all possible orderings and average them. But that's 20 factorial orderings, and 20 factorial is about 10 to the 18th, and my computer doesn't do 10 to the 18th. So we're going to be the cheap and just do 100 sample orderings and hope for the best. If this was a really professional thing, maybe I'd do more, or I'd have to figure out how many do I need. But for pedagogic purposes, 100 is fine. All right, and here is the code that we're going to do this experiment. That 100 is the 100 samples I'm using. I'm basically going to make a table of model prediction differences, and then we're going to use MapReduce to gather up every occasion on which it says, hey, what value did you get for number 3? What value did you get for number 5? We'll take the mean of those. We'll do a little ordering here. We're going to so that the biggest things come first, except that the baseline always comes very first. And that's going to be our feature influence. And if we do that, we now get a sense of what's important. Okay? And it's telling us that in terms of absolute value, feature 12 seems to be quite important, whereas feature 4 seems to be very unimportant. Right now, again, we want to make sure all these things, when I run it, when I add them up, that it's basically equal to the score for the inmate. Because again, I'm claiming that this is a breakdown of the score for the inmate. And hurrah, they do. And you know why people like breakdown? Because it makes a cool picture in the end. Let's look at the picture. I'm just going to use bar chart. And I'm going to use feature influence, which is this thing that I computed up here. And there's a picture of how our inmate did. You tell him, look, your baseline was about a negative 0.22. You got points for number 12. That was good. You did well on 12. But 5, not so good. You lost. 3 you came up on, and 2 you came up on, and 10 you came up on, but then you went back on 6. And after this, not really all that much matters. You got some other stuff going on. And in the end, we end up there, which is that negative 0.084. And so this is kind of a picture of breakdown. And I think that that is somewhat understandable. Maybe we could adorn the picture a little more, make some arrows so it was a little clearer. But I think that's a reasonable document to hand to someone to explain how it is that the algorithm, the actual deployed model, got to the result it did. Now, I just did this to make things go fast for the 25 prisoners who were most like the inmate. I could do it for everybody and see how everyone changed. I'm going to do that here. I'm going to pause the video. And my recollection is this takes about a minute to do, and this is potentially an issue if you have very large data sets. All right, I'll pause while it's going through it. Okay, so we're done. And you can see that some of the values are a little bit different. Like 5 is negative 0.168, whereas here 5 was negative 0.07. So using all the data does matter. But once again, we could make a picture that we could maybe show to our inmate. And here it is, and you can tell him, look, baseline score was 0.12, and it's number 5 that really killed you. Yeah, you picked up on 12, but then you fell down on 1. And tell a story and maybe explain to the inmate kind of what the deployed model was doing. And the virtue of it is that it provides an attractive picture. And if certain features don't have much importance, like you could basically leave this stuff out and basically say, you know, from here to here, really not much happened. And we end up with your score of negative 0.084. But there are some serious problems with the method. The main problem is it's not true. It's not what's going on. It's a method that's been brilliantly crafted to look as if it's true. The second problem is it's not deterministic. If I ran this again, I'd get the variables introduced in a different order, and our results would be different. Now, they might not be much different if I'm using, 200, 300 samples, but the problem is as I increase the number of samples in order to reduce the variation, I start to take a fair amount of computing time. And if we've got a lot of data, that computing time might not be trivial. Third, what happens when inmates compare their pictures? They're going to see inconsistencies because this kind of looks like a point score. Like you got this score on number 5, and here's how we weighted, and here's where you got. But because these models are local, they're not going to give the same answer for each inmate. And so that could lead to people getting kind of upset. Moreover, it doesn't even have to be the same person. Imagine the inmate who says, oh, I got nailed on factor 5. I really need to improve that if I'm going to get parole. And maybe they do improve it, and now they get a new score, and now factor 5 is being weighed differently. Why? Because there's a new set of neighboring inmates, and so we're not going to get the same scores. That inmate may feel that they're chasing a moving target and that the whole thing is arbitrary or a trap. The central problem, again, is that the explanation is an attractive lie. All right. There are other methods of doing XAI. One might be global lasso. You remember lasso? It's that method where we punish the coefficients in a regression, and that tends to make the coefficients smaller. Some of the coefficients, in fact, go to 0, and then we can just drop that feature out of the data set. So let's see if Lasso can predict what our neural network is doing. I'm going to use fit to do this, which we did talk about a little bit way back when. I'm going to use a slightly different form of it. What I'm going to do is form a design matrix, which is basically I'm going to stick a 1 in front of all the features, and that way I'm going to have something that can serve as a basis function for the intercept term, and then I'll have the augmented features here, I'll have the targets here, and I'll just say fit design matrix targets, and that's going to produce the coefficients of the model. So we do that. We get our coefficients, and then we might want to say, hey, how well does our model do on predicting the data? We'll use an R-squared measurement. So we'll take our augmented features, we'll dot it with these coefficient values up here, and we'll compare that to what happens when we run the deployed model against our features. And we get an R-squared of about 0.53. That's not bad. It's not great, not bad. But the problem is we still have a model with 20 features in it, and people have trouble dealing with models with 20 features. So what we could do is use Lasso to start cutting features out that aren't as important. And so that's what this code does here. We're going to just keep increasing the Lasso weight 0, 10, 20, 30, 40, and see what happens to the accuracy of our model and the number of features in the model. So we do that. And the problem is that in order to get it down to like maybe 6 variables, which is kind of what people feel comfortable with, got an R-squared of 0.23, 0.24. That's really not good enough. That's a pretty loose correlation between the emulator we're developing here and the deployed model. So this global lasso, I think we rule that out. But there are people who think, well, you don't need to use global lasso. Just take people who are like the inmate. Use them and try to do a linear model on them, because the function might be highly nonlinear if you view it globally, but maybe in a little neighborhood it's kind of linear. And so then Lasso would work well. And so if you hear about something called LIME, this is basically what LIME is about. The real LIME is a little more complicated than what I'm doing, but not all that much. And so I'm going to try to explain it to you. And actually, one of my goals in this video is to try to come up with XAI, which is explainable XAI. And one of the concerns I have about this area is that, explaining how you built the emulator is itself incredibly difficult. And so the fact that you end up with a simple model in the end may not be a lot of comfort when the person says, well, how'd you build the emulator? In any event, let's see how we do. So what we're going to do is we're going to develop a nearest function on everyone in the data set plus the inmate themselves, so that when we ask who's the nearest person to the inmate themselves pops up. All right, we do that. Here's a little function that's going to give us the position in this list here of where the k nearest neighbors are. And then what I'm going to do is the following. And this is a little bit of a kludge or a hack, but here's what we got to do. I want to make sure that our model, our emulator, at least predicts the inmate well, that the score the emulator gives the inmate is pretty darn close to what the real model gives the inmate, because if not, I think that emulator is going to lose a lot of credibility. It can't even predict my score. So the way we're going to cope with that is we're just going to include a lot of copies of the inmate in the data, and that's going to mean that our fitting algorithm is going to make pretty darn sure that it hits the inmate well, because otherwise its squared error is going to be pretty large. So this replicate nth thing, that's what this is designed to do. Maybe you could look at that and see how it operates. And then we've got this ugly piece of code here. And here's the idea, which is we're going to do Lasso on this data which has been heavily weighted in favor of the inmate themselves. But then when we calculate the R squared value, we don't want to take that weighting into account. And so we've got a little bit of complexity here, which basically stems from the fact that none of the Wolfram commands quite do both Lasso and weighting at the same time. They do one or the other. And so we got to do a little bit of hackery to get it to do both. But let's run that. And here's what we see. We see that if I get to use all 20 variables plus the intercept term, I can get a nice R squared, but I still got 20 variables. By the time I get ourselves down to 7 variables, it's not looking so good. That R squared is 0.31. It's really not very credible. That's not high enough to say that it's emulating the deployed model well. And so I don't think Lime's doing so well. Now, it is doing decently at predicting the inmate themselves. I did get that, right? We're supposed to get negative 0.084, and certainly when I don't use any regularization, I'm getting close. Here's what I'm supposed to be getting. When I look at even the third model here in my table, where I've got it down to 7 variables, we're going to see already that we're starting to stray a little bit from the true prediction or the true value for the inmate. So, so far this implementation isn't doing so well, but let's try something else. And here's the problem that we're dealing with. If the data is sparse, there's not that many inmates, and a lot of features, then if I have to have enough people in my data set so I can actually do linear regression, I got to take people that are pretty far away from the inmate, and I'm almost starting to get like global Lasso again. So here's an idea. Let's learn the distribution of people who are near the inmate. We'll use our friend learn distribution, which we studied in the unsupervised learning segment, to do that. So we get a distribution. And now, let's produce 100,000 fake inmates who are kind of like our inmate. And now, let's pick the 250 closest ones. So we've sort of artificially increased the density of the population that's like the inmate. So we've got a 250 by 20 matrix, and now we're going to do basically the same thing with Lasso, and we're just going to increase the weight of the Lasso, and let's see if this fixes the problem. And It helps maybe a little bit, but again, when we get down to 6 variables, we got an r squared of 0.39. It's not real satisfactory. And so, at least my home-built Lime is, I would say, not doing a great job at explaining what the deployed model is doing. Well, so far I used multilinear regression to try and develop an XAI model, and I did that because it's basically a point system, and people understand point systems. But there's another way we could develop a simple formula, and that's to use symbolic regression. We studied symbolic regression earlier in the course. For those of you who didn't see that or don't recall, you might want to read or reread the notebook and look at the video. But one of the virtues of this method of machine learning is that it develops explicable formulas, particularly if we restrict the type of operators that symbolic regression can use. Moreover, we can tell symbolic regression to focus on just a few variables. And so maybe it's a low bias enough method that it can explain the behavior of the deployed algorithm, which is a big algorithm also, with respect to neighboring points. So let's load in Data Modeler. That's the package that implements symbolic regression. And then I'm going to run symbolic regression here. I'm going to use that weighting method where I make sure that we're counting our inmate themselves a lot, so at least our model predicts that well. I'll say go for 2 minutes, and this little piece of code here says you're only allowed to use the 4 function calculator things: plus, minus, multiply, divide. All right, and I want you to assume that I ran that at some earlier point. I exported the results to a file, and now I'm going to re-import those. Okay, so let's bring those in. Okay, so we've got a bunch of models. Let's look at the Pareto front plot of that. And you remember that in a Pareto front plot, we're looking on the x-axis at the complexity of the model, on the y-axis at this metric of error, which is 1 minus r squared, and you've got in red the points on the Pareto front, which are these points where you can't improve both. You can't reduce complexity and reduce error. There's nothing that's going to do that. Now, you can prefer one or the other and move along the Pareto front, but you can't move down and to the left. All right, so let's actually find the models that are on the Pareto front. And now what we want to do is we want to take a look at all those models. We're going to look at what's called their dimensionality, which is how many variables they have, their complexity, which is a special metric that the data modeler people use to see how complicated their model is. It's a pretty good metric, I feel. We're going to look at the r squared value, footnote, and then we're going to see how well does it predict the subject. The footnote here is while I built the model by overweighting the inmate, I want to compute the r squared without overweighting. And there's a little bit of code here that I've written that does that trick. I don't think I need to go into it. And now let's take our Pareto front models and build a little data set showing these scores, and I'm going to sort them high to low by their r squared value. And here we are. And what you see is we did pretty well. We've got r squareds of 0.91. We're predicting the subject's value pretty well. Yeah, there are a few that I'm not so happy with, but they're not too bad when we're trying to get negative 0.084. And yeah, these formulas, these are too complicated. But let's look at something like this formula. This formula is, we've only got 5 variables. We're only using addition, multiplication, and division. We're getting fairly close and predicting what the inmate gets. And we got an r squared of 0.81. Or if that's too complicated, maybe let's look at this model. We only have 4 features. Anyone can do 4 features. Got an r squared of 0.78, and we're predicting that inmate pretty well. And, we can go down to even simpler models, and their r squared is way better than what we were seeing for the alternative. So I say symbolic regression's doing quite well. There's a story that can be told to the inmate that uses just a few variables, and the most complex operations are addition, division, multiplication, subtraction, and we're getting an R squared of over 0.7. Now, these models may be overfitting, but replicability has not been an emphasis of XAI. Rather, the emphasis is on telling a comprehensible story, even if that story happens not to be particularly true. Is this a fluke? No. I've tested this on other sample situations, and the result I've shown you is pretty representative. Symbolic regression does pretty well in coming up with a fairly straightforward formula that can predict what our deployed model is doing. There are other components of Data Modeler that help with the interpretation of models, help simplify models, but those are subjects for a more advanced exploration of its capabilities and for another video that maybe I will produce one day. Is it perfect? No. These are all lies. These are not true. Moreover, the formulas are going to be different for different inmates. So we got the same kind of issues that I discussed before, but at least we have something relatively simple that predicts in general pretty well and predicts the inmate pretty well. Some people have also suggested using shallow decision trees as a way of emulating the complex function. I'm going to make this real short. As far as I can see, didn't work well here at all. So I don't think we need to cover it. I think we've seen methods that do better, and for now I don't recommend that you use a shallow decision tree as an emulator. Well, we've seen in this course how very elaborate models can end up creating decent classifiers or predictors. And in many settings, a black box that works might be all you need. They're likely to work considerably better than human intuition. The challenge of XAI comes when humans demand an explanation they can understand. Because we're in the infancy of bridging technology, and unfortunately my suspicion is that we may not actually get that far. Humans and machines think very differently, or at least humans' understanding of their own thought processes, which I suspect that introspection is pretty limited, is very different from the way that machines work. Yes, we can come up with just so stories that serve as a simplification of what the machine's doing. And maybe they'll pacify some demands for an explanation. But until humans and machines converge in their thought processes, which I think could be a long time, explaining truthfully to a human what the machine did is likely to be as confusing as explaining to the machine what the human did. Thanks for your attention. Hi, I actually am Professor Seth Chandler, Professor of Law at the University of Houston Law Center, and this marks the end for spring 2021 of Analytic Methods for Lawyers, a course that spanned now 50 videos that consume about 40 hours. I really hope that you've enjoyed at least some of it along the way. I know that you have learned a lot. And I also know that in some ways we're not done. You are going to see the materials that we've covered. Maybe not in your practice, maybe not in your job, maybe, but you will see it in your life. You're going to see the issues that are discussed here, some of the technologies that are discussed here arise over the next years. I can't tell you what's going to happen in 20 years, but certainly in the near-term future, the materials we've covered are going to be relevant. But I'm not here to preach that. What I'm really hoping to let you know is that we're not done in another way. I certainly hope that one day we will be through this dreadful pandemic, and that at least some of us will be able to reminisce fondly in person over what we were able to learn in this course. And so with that, I wish you well, and I wish you goodbye. Thanks.